Hello learners, welcome to this course on practical machine learning using Google Colab. In this tutorial, I will be describing about an image descriptor called as local binary pattern. So this image descriptor gives the texture information about an image. So let us talk much detail about this local binary pattern. So local binary pattern is used to characterize the texture and pattern in an image. So it computes the local representation of the texture. The local representation is performed by comparing each pixel with its surrounding neighborhood of pixel values. So thereby we get the local representation of the texture. So these LBPs are implemented in Mahotas package as well as in a scikit image package. So I prefer scikit image because it is easier to use, and also the recent extensions has the capability of expanding the neighborhood size. So thereby the large area details can also be obtained. So we will try to see what are all the steps involved in your local binary pattern. So the first step is constructing a LBP texture descriptor by converting our image to a grayscale. So first we try to convert our image to a grayscale. Then for each pixel in the grayscale image, we select a neighborhood of size R surrounding the center pixel. Then we do some simple pixel test, thereby we estimate the LBP value. So the LBP value which is computed is stored in a output 2-dimension array. Now let us see how to calculate this LBP value in detail. So let us take an image with these values, and this is our center pixel. So this is our neighborhood, 3 by 3 neighborhood. So what we do is we compare our center pixel value with the neighborhood. So if my center pixel value is greater than my neighborhood value, we assign 1 to that position. If my center pixel value is less than the neighborhood, we assign 0 to that position. So when I compare this 4 with 1, 4 is greater than 1, which means I put 1 here. Same way 4 is greater than 1, so we assign 1. 4 is greater than 2, we assign 1. So here if you see 4 is less than 7, which means the center pixel is smaller than the neighborhood, so we put 0 here. Same way 4 is greater than 3, 1. 4 is less than 5, we put 0. 4 is less than 5, again we put 0. 4 is less than 8, we put 0. So we get this value for the neighborhoods. So now what we do is we try to assign these values with each position. So if I consider this pixel to be at 2 power 0 and this one at 2 power 1, 2 power 2, so like that it goes on. This is 2 power 3. So like that it goes on till 2 power 7. So when I assign this value, by assigning the position of these values, I can estimate a value. So for example, here I have given 0, 0, 0, 1, 0, 1, 1, 1. So if I put the value here, you will get a value of about 23. So this 23 is substituted instead of your center pixel value, and this image is called as a LBP image. Similarly, I can move this window, this neighborhood to the next subsequent pixel. Again I can do the same computation. Thereby I get again another value. Let me take another example. So if the next pixel is something like 1, 1, 2, so 5, 6, 7, 8, 4, 7. So let us assume that I have moved this window towards right by 1 pixel. Then I get this value. So in this case what will happen? Again, if I construct it an LBP image, So I have to see whether my center pixel value is greater than or less than the neighborhood. If it is greater than neighborhood, we have to put 1. So here in this case, 1 is less than 6, so we put 0. 1 is less than 5, 1 is less than 7, 1 is less than 2, 1 is less than 7, 1 is less than 4, 1 is less than 8. So in case of 1 is equal to 1, in that case, we can make an assumption that I can put 0 or 1. So here I am going to take, if 1 is equal, then we try to put it as 1. So again we have to start with the same positioning system as we have done earlier. So we have taken this pixel as 2 power 0. So here I try to take this one as 2 power 0. So like that it goes on, and finally this pixel will be at 2 power 7. So if I try to put these values, so this is 0, 0. So only 2 power 7 is 1. So I will put 1 here. Remaining all values will be 0. So this will be equal to 2 power 7. So 2 power 7 is nothing but 128. So this 128 I will try to substitute in this location. So like this we try to move the window from top left towards right, then we start moving from top to bottom. We complete it, so thereby we get an image called as output LBP image. So this LBP image is going to have a value between 0 to 255. Why? Because I take 8 neighborhoods. So I take 8 neighborhoods, so my value can vary from 0 to 255 to the max. Right? So this LBP gives the texture information of an image. So here if I consider, when I consider a pattern, whether it is uniform or not uniform, we can declare it. When a pattern is said to be uniform, if it has at most 2 0 to 1 or 1 to 0 transitions, then that particular pattern is called as a uniform pattern. So when we look at this pattern, okay, if I take this pattern, so here all are zeros, then I have a transition here from 0 to 1, then again from 1 to 0 I have another transition. So 2 transitions are there in this pattern. So we have only 2 transitions, whereas in the second case I have only 1 transition. 1 to 0 transition is there, and then again the pattern remains same. So 1 transition. So like this, if I have only 1 or 2 transitions, then such patterns are called as uniform pattern. For example, if I take this combination, so there is one pattern here, 0 to 1 transition, 1 to 0 another transition, again 0 to 1, again 1 to 0, again 0 to 1, 1 to 0. So altogether 6 transitions are there. So such patterns are called as non-uniform patterns. So these are called as non-uniform patterns. So by constructing this uniform and non-uniform patterns, we can construct an histogram out of it. So thereby that histogram can be used as a feature vector. So that is the algorithm behind your local binary pattern. So we try to find how many uniform patterns are there, how many non-uniform patterns are there, and by using the uniform and non-uniform patterns, we try to construct an histogram. So thereby a feature vector is developed using a local binary pattern. Now let us see the primary benefits of this local binary pattern. So there are 2 primary benefits. One is we are examining the simple 3 by 3 neighborhood. We are taking a small neighborhood. So thereby we are processing it at a very faster rate. So this algorithm is extremely fast and also efficient. So we try to do only pixel test. We are not doing any complex mathematical operation. So it is quite fast and it is quite good also. It only requires a simple thresholding technique. Whether my center pixel is greater than neighborhood, then we assign 1. If my center pixel is smaller than neighborhood, then we assign 0. So just a simple thresholding technique will be used. The second benefit is this algorithm works at small scale, which means even a small intensity variation, texture variation, it can be easily captured. And this also becomes the drawback of the algorithm. Why? Because since we are working at a very small scale, larger variation of information cannot be obtained. The variation of image or variation at a larger scale, it cannot be acquired by this algorithm. So to handle this, we have an extension of an LBP implementation. So here what we do, instead of using a square neighborhood, we go for a circular neighborhood. So in circular neighborhood, what I can do is I can increase the radius of the circle. If I increase the radius of the circle, what happens? Larger area can be covered. So when I increase the radius of the circle, then I should consider how many points I am going to take on the periphery of the circle. So that also plays a vital role. If I take very less number of points on the periphery of the circle, then we will not be able to get the correct texture information. So I should have an optimum number of points around the periphery of the circle, so thereby I get the maximum information from the image. So two parameters are introduced. First is the number of points in a circular symmetric neighborhood. So when I take a circular neighborhood, how many points I am going to take? So the number of points P which I want to consider in my circular neighborhood is very important. The second parameter is the radius of the circle. If I have a small radius, I can't accommodate more number of points. If my circle is very big, then again, if I put more number of points, I can get more information, but it will also have a memory constraint issue will be there. So we have to select the optimum number of radius and optimum number of points in the circle. So usually what we do is we try to consider how many uniform patterns are there in our neighborhood. So for example, if I take a circular neighborhood and I am going to consider 8 points in my neighborhood. So if I take 8 points, so here P value is going to be 8. If I take P value to be 8, then in that case, how many number of uniform patterns I can have? So if you see this image, the first row represents 9 patterns. So this first row represents 9 patterns. So in this 9 patterns, you can see one transition or 2 transitions at most. So here you can see the center pixel is here in the 0 pattern. All the neighborhood pixels are black. Black means 0. This circle represents 1. Normal circle represents 1. Black circle represents 0. So here there is no transition at all in 0 pattern. Whereas in 1 pattern there are 2 transitions, 0 to 1 transition, 1 to 0 transition. In pattern 2 also 0 to 1 transition, again it remains 1, and from 1 to 0 transition. In pattern 3 also 0 to 1 transition, and then again from 1 to 0 transition. So if you look at the first row, I have 1 transition or 2 transition or no transition. So such patterns are called as uniform patterns. Uniform pattern. Other patterns, second row, third row, fourth row, I have 27 patterns here. So this 27 patterns, if you look at it, it has more than 2 transitions. For example, let us take this pattern. I have 0 to 1 transition here, 1 to 0 transition here, again 0 to 1 transition, 1 to 0 transition. So I have 1, 2, 3, 4 transitions are there. So such patterns are called as non-uniform patterns. Non-uniform patterns. So if altogether I have 36 patterns, out of this 36 patterns, 9 patterns are uniform patterns, remaining 27 patterns are non-uniform patterns. Then how to calculate if I increase the number of P value? So for P value equal to 8, I have this combination. So if my P value is 12, how to calculate the number of uniform pattern? There is a simple logic here. So if I have p value 8, the number of uniform pattern is 9, which means p plus 1. So uniform pattern is equal to p plus 1. We can just take it as p plus 1. So here what I can do, if my p value is 12, then uniform pattern will be about p plus 1, which is nothing but 13 patterns. So 13 patterns will be there as a uniform pattern. So as a simple rule, we can use this formula to calculate the number of uniform pattern. So while computing the histogram, what we do is we put the patterns, uniform patterns or patterns along the x-axis. So I have pattern 0, 1, 2, 3. So like that it goes on till 8. Then all the other patterns, all the non-uniform patterns can be combined. It can be combined and put it as one pattern. So these are the bins. These are the bins in your histogram. So now what I can do in my image, how many 0 patterns are available, that I can compute. How many 1 patterns are available, how many 2 patterns are available in my image, 3, 4, 5. So this till this 8 it is uniform pattern and 9 is non-uniform pattern. So I can construct an histogram. I can construct an histogram out of this. So which means I have how many bins here? For my p equal to 8, I have 9 uniform patterns plus 10th bin is your non-uniform patterns. So altogether I have 10 bins. 10 bins in my histogram. So what will be the size of my feature vector? So feature vector will have 10 elements. So like that I have 10 elements. So what does this first element represent? Number of times this 0 pattern has occurred. The number of times the first pattern has occurred. Same way number of times the second pattern has occurred. So like that number of times the non-uniform pattern has occurred. So all these details are represented by a feature vector. Now this is done for a local neighborhood. So in order to preserve the spatial information, what we can do is we can take an image. So I can take an image, divide this image into small sections. I can compute a LBP for this section, LBP for each sections. Then what I can do, the final feature vector is obtained by concatenating all the LBPs. So final vector can be obtained, and this is something like a optional step, right? So this also we can do. So this will preserve the spatial information, because one LBP gives the information about this region, another LBP gives information about this region, another LBP gives about this one, and another LBP gives about the bottom right region. So like this also we can calculate the LBP patterns. So here the important aspect is here, if my p value is 12, how many uniform patterns I will have? So uniform patterns will be p plus 1, which is equal to 13 patterns I will have. So non-uniform pattern, we combine all the non-uniform patterns and make it as 1. So how many bins in my histogram? So bins is equal to p plus 2. Why p plus 2? Because p plus 1 is your uniform pattern plus one additional pattern for your non-uniform patterns. So it will be P plus 2. So that is 14 bins we try to take. So our feature vector dimension will be of 14 dimension feature vector. Right. So this is how we try to calculate the feature vector for our LBP. So now let us look at an example where we try to use the local binary pattern to implement a mini fashion search engine. So mini fashion search engine means we try to rank the pieces of clothing for similarity based on texture. So what we do is we take certain images. I am going to take some shirt images and I am going to extract the LBP patterns from the shirt images and save it in the database. Then I am going to take some images as the query image. Again I am going to extract the LBP pattern and I am going to compare this pattern with the already existing pattern in our database. Then I am trying to return the top 3 ranked shirt images with similar texture content. The algorithm will try to return it. So that is what we are going to do in the mini fashion search engine. We are going to rank the pieces of clothing for similarity based on texture. So let us try to import the necessary packages. Print function. IMutils is a third-party library which we try to use it for getting the path of the images. Then cv2_imshow is used for visualizing the images. NumPy is a matrix library, numerical Python library. cv2 is a computer vision. Image processing algorithms are available. Then the LBP features are available in the SK image package. From that I try to import the features. So let me execute this. Next, after importing all the necessary packages, I try to create a dictionary of index. So this dictionary is where I am going to put all the LBP features. So in order to put the LBP features, I have to create a file name. So file name will be used as a key for this dictionary. So for this key, this is the feature. For the second key, this is the feature. So like that we are trying to create a dictionary out of this. So right now it is empty. So I put it as open parenthesis, close parenthesis. Then I am trying to define the radius of my neighborhood. So I am going to take the radius as 8. And how many points I am going to consider in the neighborhood? I am going to consider 24 points in the neighborhood. So which means my number of points which I am going to consider is 24. So my p value is 24. Which means number of uniform pattern I am going to have is going to be 25. So how many bins I am going to have in my histogram? Total 26 bins I am going to have. Why 26? Each bin for a uniform pattern. So 25 bins will go for uniform pattern and then one extra bin for all the non-uniform patterns. So that is how we get 26 bins in the histogram. So what will be the feature vector size? Feature vector size will be 26 dimension feature vector. Now let me describe the function to extract the LBP features. So here we use the function feature.localBinaryPattern. So here we give some parameters like image I have to give, for which image we are going to find LBP, and number of points. So number of points is 24, radius is 8, and we specify the method uniform, means I am going to consider the uniform patterns and all the other non-uniform patterns will be considered as 1. So that is how we get this LBP. So the LBP, what does it have? It has a 2-dimension information. So for example, if this is my output LBP, this is my output LBP image. So what it will contain? So it will contain the values between 0 to 26. Why 0 to 26? It will try to see whether this pixel is a uniform pattern or not. If this is a uniform pattern, so I have maximum of 25 uniform patterns. 25 uniform pattern plus 1 pattern for non-uniform. So that I can keep it as, so this 25 uniform pattern I can number from 0 to 24. So this non-uniform pattern I can give the name as 25. So if this pixel forms a uniform pattern 4, let us assume I will put 4 here. Then the next pixel is 5. Next pixel, if it comes under non-uniform pattern, then it might be 25. So like this, depending upon the patterns in an image, each pixel will be given the value between 0 to 25, where 0 to 24 represents uniform patterns and 25 value represents it's a non-uniform pattern. So this is how the output of an LBP is going to be there. So I have to convert this 2 dimension into a 1 dimension, then only I can compute the histogram. So for that, what we do, we convert our LBP into a flattened array using this Ravel function. So this Ravel function will try to make it as a flattened array. Then we try to give the histogram function. So thereby I try to compute how many times a particular pattern gets repeated on an image. So that we try to estimate using np.histogram function. So what are all the parameters we give? Bins. Bins is nothing but how many bins? From 0 to num point. Num point is 24. 24 plus 3, it is 27. So remember, in Python, the stop value will not be included. So our range is varying from 0 to 26. So 0 to 25 is for uniform pattern and 26 is for non-uniform pattern. And then I have something like range from 0 to 26. Again, the range of values will be from 0 to 25, which will be available in your LBP. So thereby we compute the histogram here. So after computing the histogram, if we want, we can normalize the histogram. So normalization is very important because it can account for variation in input image sizes. Because in certain image, number of pixels can be more. In some images, the number of pixels can be less. So in order to make it uniform, it is always better to do the normalization step. So once this is done, after extracting the features, we take an image from our path, read that image, convert that image to a grayscale image, then I try to compute the histogram for that grayscale image. Once the histogram is computed, I try to get the file path name. Then in the index dictionary, I am going to put the key as a file name and the histogram as the LBP value. So for this file name, this is the value. So like that, the for loop runs for all the images in my data set. So thereby it creates an index. So let me show you the images in my data set. So I have two folders, shirts and queries. So shirts are the database images. So here I have 10 types of shirts. So you can see the pattern varies. Shirt underscore 01, this plain shirt, this is a checked shirt. You can see the pattern varies. So now we are going to rank the images based upon this pattern. We are not going to consider color, we are going to consider the pattern. So in terms of a query image, you see, I am going to take 3 images, query underscore 01, 02 and 03. So depending upon the pattern, this is a 01, 02, 03. Based upon the pattern, a suitable images from the data set is going to be returned by our mini fashion search engine. So now we try to take the query image. So I am going to take the query image as query underscore 01. Then for this query image, again we compute the LBP values, show the query image here. First let me run this section. Here you can see, while training, for each image you see So for this image, for the first image, you can see here, this is for the first image, you can see the feature vector. So the feature vector contains 26 elements. Feature vector contains 26 elements. So 26 dimension feature vector. So like that, for each image we have a 26 dimension feature vector. So when I execute this section, you can see this is the query image which we are giving. We have to find the similar texture in the shirts folder. So now I am going to take one by one, right? So I am going to take from my data set. Index is my dictionary. So from the dictionary I am going to take the file name and its features both, and I am going to compute. I need to compare two images. How to compute two images? I can use some distance metric. So here I am going to use chi-squared distance metric. So chi-squared distance metric, how we can compute this? 0.5 into sum of features minus query features. Features is nothing but the features available in the database. Query feature is the features obtained for a query image. So features minus query features square 2 divided by features plus query features. So we try to compute the distance value. If the distance is small, then the two images are similar in texture. If the distance is large, then the two images are dissimilar. So after computing the D, I try to store that result in a result dictionary. So this is what happens between a query image and already available feature in the database. So like this, the query image is compared with all the 10 images features in the database, and then the results are stored in the results dictionary. So once it is done, we try to take, so here you see this is the distance metric. Query image with the first image, second image, third image. So like that we try to compute. Then finally I try to show the top 3 ranked images. So that is given by this :3. So top 3 ranked images are taken. So the first top ranked image has a distance value of 0.0073. Which is that image? So that is this shirt_02. Shirt_02 is very close to the query image. Then what happens? The next value is 0.0118. So this value is obtained by comparing the query image with the shirt_03 image. So like that, the third best one is 0.0153. So this is for your shirt_04 image. So these are the top 3 ranked images. So we try to plot those images and see using this code the top 3 ranked images. You can see this is for shirt_02. Shirt_02 is this one, and it has a distance value of 0.0073, and shirt_03 is 0.0119. This is the second best match. Same way, shirt_04 is the third best match. So this is how a simple fashion search engine can be developed using a local binary pattern method. So in this tutorial, I have described about local binary pattern and how it can be used for making a mini fashion search engine. Thanks for watching. Please subscribe for more technical learning. You can find the code at the link given below in the GitHub repository. Thank you.